Hi, thanks for coming to my talk. And yeah, we're going to be talking about Skycache. What is the problem that we're trying to solve? I'm going to make this talk kind of like assuming very little knowledge, right? So I'll be going over some things that you probably, most people in this room may already know. So when you run a Bazel command for the first time, it spins up a server in a cold state on that machine. And then it does a so-called clean or cold build, which parses all the build files and does all the execution. And this is very, very slow, especially for large builds. It can be like more than 10 minutes. This is lost developer time and productivity, and also, at scale, this is a lot of computations being done redundantly because every single Bazel instance is doing the same computation if they're working on similar targets, and that does happen in our systems. So what is Skycache? Skycache is a cache that pretty much caches all of the analysis and execution state for a Bazel server, and arbitrarily large targets have build times reduced to about 20 seconds. And then it's way less memory usage because we're not like pulling the entire state of the build graph into memory, but only like the top part of the graph that is needed to just get the results. It's very similar to, in a sense, to like build without the bytes, like only outputting like the top level run files. And we want to make cold builds obsolete. Okay. To understand how Skycache works, I'm going to have to talk a little bit about Skyframe. This is the internal data structure, so the internal framework that Bazel uses that drives all the computations. Skyframe is actually conceptually very simple. It's a bunch of Sky functions with static definitions. They're functions. There's some concurrency, but it's a bit. I'm going to declare that's an implementation detail. And then there are Sky keys. A Sky key is basically a function name plus its parameters. And then Sky functions can call each other recursively. So you can get these really nice build graphs. Sorry, one more point on this slide. Sky keys and Sky values are serializable. We have custom serialization code that works on all execution and analysis values. So here's an example Skyframe graph. You see sort of the usual suspects here. You see action execution near the top of the graph, and then you may see something like a configure target or a package and a file. Configure targets are the sort of the outputs of the analysis phase, and packages are this sort of phase that encapsulates the computation done when parsing a build file. So Skycache has three main concepts. One is top-down pruning, and one is this invalidation using sort of the sets of file dependencies of every single target. And then there's a lot of work done to make the serialization of this stuff efficient. So top-down pruning is basically, so this is like a very, very abstract Skyframe graph. Basically, when you get a cache hit from Skycache, you don't have to pull anything from underneath, right? Because the top-level Sky function doesn't directly depend on those transitive dependencies. It doesn't need to look at those Sky values. So you can just, when you get a Skycache hit, you just throw away everything underneath it. So in terms of the cost-benefit, this is somewhat interesting. If you were to deserialize the entire analysis phase, I don't think there would be much benefit because that cost of deserializing is not going to be like much better than the cost of computing it locally. So all the savings you see are from that top-down pruning. Instead of loading hundreds of thousands of nodes, maybe you only load thousands of nodes. right, as remote cache hits. Okay, in order to prove that you actually have a cache hit, you have to be able to sort out the values that are considered fresh in the cache versus the ones that are stale. And for that purpose, for every single target that we cache, we store all of its transitive file dependencies in this sort of nested structure. And then we look at the files in the client that are modified. I'm going to put this in terms of Git. Like, let's say you have a commit hash that you're based off of. Then you do a git diff, and you find which files have changed relative to that baseline, and that's a set M. And then F is something that was previously persisted at that commit hash that was stored in Skycache. And if there's any overlap, then you know it's a stale value. And if there's no overlap, you get a cache hit. These dependency sets have this interesting structure. If you're familiar with something called a nested set, which is one of the foundational data structures of Blaze, file dependency sets have a very, very similar structure. There are two concepts. There's a node, and then there's like a source node. So nodes store the dependencies of the analysis targets, and the sources store the dependencies of execution. And we do track them separately, but they form this sort of nested graph where the data is shared. So because T depends on T1, it means if T1 is invalidated, then T is invalidated. So it has this, it transitively, the set of dependencies of T include the transitive dependencies of T1, right? But they can share memory. So it's a bit more efficient. It's much more efficient than storing all of the sets explicitly in a flattened way. Okay, so a naive sort of Java serialization-like approach to this, which was what we did in our early attempts, proved to be very, very bad in terms of the serialized representation. There was like a 10x blow up. So you're suddenly looking at 150 gigabytes to store this build on disk, which seems like a lot. And in particular, the serialization of star-like functions was very expensive. We're basically trying to serialize the Java representation of the Python code, serialized Java representation of the Python code, which is just a little bit too much indirection, right? So for the first of these problems, you may have been able to guess this, but basically, if you serialize every single Sky value independently of the other Sky values, then you're going to serialize a lot of redundant data because they share data. Like the providers that are passed between Sky values during analysis, they're transitive info providers. So transitive data gets propagated up to up the graph, gets accumulated going up the graph. So what we do here is we have this is actually, I think, rather unique to Bazel serialization and very different from Java serialization. We have this global memoization layer. So when you think about Java serialization, you're serializing an object graph. If you encounter the same value again, then it goes in some memo table and it writes a back reference instead of repeating the object. This also solves cycles, right? But there's no concept of let's serialize value A and then serialize value B, and they share data, right? If you just naively serialize, you'll get two copies of the shared data. So we have this sort of explicit API that says, hey, let's declare this as a shared value, and then we'll serialize it once. The code is a little bit complicated because the serialization of all this stuff happens concurrently. So if two values are being serialized at the same time and they share data, then you have to deal with the concurrency. Deserialization with shared values is very treacherous relative to serialization because If you deserialize a value and you may be in a state where, let's say you're trying to deserialize this value concurrently, this shared value concurrently, you may end up in a state where that value is not yet completely deserialized, and you try to insert it into one of its parents. Then, upon seeing that incomplete value, it could try to like compute a cache code or something, and then crash. But it ends up being kind of elegant. This ends up being kind of elegantly resolved. There's a shared value graph, right? There's like this inner normal serialization graph, and then there's a shared value graph, and it's a DAG. It's directed and acyclic. And because it's a directed acyclic graph, it's a normal dependency graph, so we can just do a very, very straightforward dependency graph, parallel traversal going upwards. But we wait until all the children are done before propagating the values upstream. What happened? I lost the ability to switch my slides for some reason. Okay. I just spoke to this. There's a little bit more detail here. The object codecs are the implementations of the serialization code. It's like done on a per class basis. And there's 2 APIs that we use to allow asynchronous serialization. One is like you can declare a builder, and then the builder has to be thread safe. The asynchronous values can be set at any time. And then there's like there's this field setter version where the object itself is a mutable builder. You can imagine having an object constructed with all nulls using an unsafe API, and then the private fields being written in. That is a thread-safe operation, but that's going to go away in the future because Java is removing the ability to set final fields. Okay, and then the last piece of the puzzle, I alluded to this earlier when I talked about the serialization of Starlark functions or Starlark modules. So imagine you're trying to serialize a Starlark function, which is like this Python code that's been turned into a Java data structure representation. That ends up being very, very expensive. So instead what we do is we allow that to be represented as a Sky key pointing to its BZL load key, and plus like its global name. And that ends up being, it's just serializing a key, which is cheap. And then upon deserialization, our serialization machinery is already asynchronous. So we can do a Sky function lookup. We can call the Sky function to evaluate the BZL locally, and then pull the Starlark function out of the compiled BZL module rather than trying to deserialize it. Based on profiles we've done of builds running, loading BZL values is a relatively cheap operation compared to everything else we do. So this ends up being an effective mechanism. Oops. Okay. So enough with sort of the nitty-gritty of details of how it works. Here's some results from a dog food. So this is real-world data. It's rather limited sample size, but basically it's a small to medium target that we had asked users to try Skycache with. And so the build times went from 46 seconds down to 13 seconds. And you can see like the reduction in the actions executed, targets configured, and packages loaded. These are for the same target, and that's the effect of top-down pruning. This is a representative bounds for a large target. What I mean by lower bounds is that it's very optimistic. It's when all the caches are hot and everything is clean, right? There's no stale values. We see like a 7-minute, 21-second target go down to 17 seconds. There's a little detail here about how much time is spent in Skycache. It's only 5 seconds. And then there were some actions that are just semantically unshareable, and those are uncacheable, and that takes up the remaining 10.5 seconds. And there's 1.5 seconds of initialization code, 1 second of which I don't know how to account for. I should dig into. All right, so the limitations and future work. In terms of the limitations, it uses considerable RAM. So in the amount of, we're putting all this data in like memcache, something like memcached, and because there's a lot of these indirections, these references. Like you recall the nested structure of the file dependencies. There's a lot of references, so there's a lot of RPC hops. So we use something like memcached to avoid adding too much latency to multiple round trips over an RPC connection. And RAM is expensive. That coupled with the fact that users one of our really, really important clients wants to have very, very old versions and a high version cadence. So that means we have to persist thousands and thousands of images per target that they're interested in caching. And currently that's actually infeasible for us with at the size of those targets and how the number of them and cadence. Things that we're looking into, and this is sort of our main limitation and things we're looking into. So we've done an empirical study where we do observe, I think a lot of you may have heard of like social networks and power laws. Basically, there's a small number of nodes that have that account for an overwhelmingly large amount of the links or edges, or in this case, this comes down to like 2.5% of targets accounting for 90% of targets actually built across a very, very large set of data. So perhaps we can do some targeting of our cache based on frequency. We'd also like to look at things like dictionary-based compression or moving caches from RAM to disk. And that I think is challenging because we have to come up with a strategy for reducing the indirection. It would probably not be good to have very, very many round trips to disk, which is what Skycache would require today. So I heard that this was a question on a lot of people's minds, like how do we get Skycache to work with Git? It's built on top of Piper right now. I've identified the classes here that are the exact classes. These are all open source classes that you would have to use. There's this long version getter. You'd have to give each git commit hash an index, and then you can use git diff to find the files that have changed. If you recall how the incrementality algorithm compares the set of changed files to the set of dependencies. You can get that out of Git as well. And there's a service that we implemented there's an interface. It's the remote analysis cache client. And the class file dependency deserializer is provided. And that takes care of all the marshalling and unmarshalling of the file dependencies. And you'd have to bring your own fingerprint value store. That's just a very simple key value store. I think if I were in the open source world, I would be inclined to try Redis on Flash for that. Yeah. And that brings me to the end of my talk. Are there any questions? Yes. Okay.
Hi, appreciate for the talk. I really love the update. I tried to play around with the current implementation. And yeah, all the class you have listed out, it was suggested by Codex. So it was really handy to try to implement a Git version of it. However, I did run into problem with the protocol currently. It's very binary oriented and it's very similar to memcached. Both the key and the value are very binary. There's not a lot of things we can do with it on the server side. So if we want to extract some data and visualize the sky, for example, if we want to build some sort of visualization for the Skyframe based on that data, currently it's not possible. So is there a version in your mind where we can have something like protobuf and gRPC for serialization instead of these binary?
That's a really, really interesting question. So the question is sort of around how do you create a well-formed key for these sub-objects? Some of the objects have a natural key, like the sky keys. So you could imagine, instead of having a digest of the sky key, have the sky key explicitly there represented, but then there's sub-objects inside the sky values, right? So stuff inside the transitive info providers, for example, that are serialized with indirection, for which there is no very natural key, although it is a very interesting question, and it's one that we're thinking about. There's no current implementation. Thank you.
So you mentioned specifically that the likelihood is high that the round trip rate is significant between the client speaking for looking up what are essentially sky keys and the remote analysis cache. Can you give an order of magnitude of, is it, if I said that we had 1 million actions in our build, what is the likelihood that that translates to 1 million-ish sky keys in use, and or is it reduced by anything, or what would need to be effective for a storage protocol where we would be able to get batches of these things in sequence?
Okay, so okay. There's a couple questions in there. Let me ask. Let me just take care of the easy one first. The batching, we do tons and tons of batching. Everything is batched extensively in our low-level communication protocols. The second, the more interesting question, the more elaborate question to get into is the proportionality between the size of the build and the amount of data, the number of round trips. Because of that top-down pruning property, it may be something like OC, right? It may be like constant order. Maybe you only need 10,000 keys, no matter what. Based on your project, right? Because there's going to be a locality, like some people are going to be working in this section of code, and they're going to make changes there, and then you don't really care about stuff outside, all the stuff outside. So this is just like serialization along that boundary. If that makes sense.
Thank you.
Hi, great talk. Super interesting to see progress in this area. So I was wondering, you were showing before where you had the transform. Can you hear me properly?
I can't hear you. Can you step up a little?
Yeah. So great talk. So earlier in the presentation, you showed the graph where you did the transform from the cyclic graph of action keys into the directed acyclic graph.
Yeah. This.
Yeah, so I was wondering, how do you resolve because that's not like a, how am I going to put this, it's not like a canonical transform or something. When you get a secondary build, how stable is the shared graphs part going to be compared to the first build, etc.?
That ends up being a super interesting question. Because of the semantics of serialization, what you get is value equivalence, but you don't get structural equivalence. This has been us a couple times. It's believed that, we believe that in all the places where the structure matters and you have value equivalence, we can work around it. Like there's a workaround inside the nested set where the nested set may not have the same structure as the one that you actually serialized, like the same reference structure, but it has the same value structure. Like if you iterate over if you flatten the nested set, you get the same values back. But there's like a little hack in there to make sure that it happens even if the structures change.
All right. Thank you.
Welcome.
You mentioned you do top-down pruning, right, for caching. Do you ever get into correctness issues with top-down pruning? Like I imagine you use top-down pruning for like caching actions, but you could, because of say like non-determinism, then get, potentially into like incorrect builds because of, yeah, I'm curious.
That's a very interesting question. There is this theoretical edge case where you have two non-deterministic builds that wrote the cache of the same target, and you can get a chimera. Okay, so you get like this build that built using one non-deterministic value at the bottom. You get this other build that built the same target with a different non-deterministic value at the bottom, and then they'll merge and they'll become something novel, which is not great. Yeah, that is a theoretical possibility. We've been running a system like this for many years, and it hasn't come up even though, even though it's theoretically possible.
Okay, I see. And then I had a second question about, I saw there were like non-cacheable actions in the build, right? I assume you also don't do top-down pruning for them, but or Skycache for them. But what about like the parents of non-cacheable things that could be cacheable? Like, do you still use Skycache for those as well, or is it like anything that depends on non-cacheable is always also non-cacheable?
I think the correct thing to do would be to not serialize the stuff that is downstream of something non-cacheable.
Mm-hmm.
I think it works. I'm not 100% sure. The code is correct.
Okay, thank you.
Yeah, sure.
I would imagine that the impacts of like Skyframe caching would be disproportionately felt by super large monorepos where like it's impractical to do analysis on the entire like transitive closure. But for more medium-sized repos, has the Bazel team explored like making Starlark run faster, like JIT compiling Starlark or doing things like that, so that like it's so fast to run Starlark that we don't need to cache analysis?
There's probably people in this room that have a better answer to that than me. But
okay.
Yes, there's definitely work being done in that area. Does anybody want to chime in on that one?
Well, I'd say the topic has come up every time we benchmark things. The core Starlock execution isn't a bottleneck as everything else. It's certainly been on our list, and maybe if it looks like a way, we'll come back to it.
I hope I'm not opening a can of worms. I know very little about Bazel internals. I'm just curious. Thank you.
Thanks. Okay. Thanks again for coming to my talk. I think that's all the questions.